Okay, so in this week 2 session, a lot of concepts were discussed. The content quantity was a lot, but there were a lot of things that may, if for a beginner, it may be a little bit frightening, or a little bit overwhelming to know all those things. Not all the things are required at this point of time. So we'll be discussing some main concepts that will be useful for solving your assignments. I think the assignments for week 2 assignments were already released, but still, it will these things will help you out in in the coming exams also. So we'll discuss some of the main concepts. We'll not go into the very detailed explanation of some of the things that as of now we don't need. Okay, so let's start. So can anyone tell me, what we have done till now, or what we have seen till now? We all would have seen this, that what we are trying to do is we are trying to fit some kind of a relationship. So I will be using OneNote for this session and from now onwards, because last time my handwriting was not that well, so it will be problematic for you guys to understand. So instead of PPT, we'll be using notes to discuss. Okay, so what we are trying to do in machine learning, we are actually trying to fit a relationship between input, let's denote it by X, and output, let's denote it by Y. Now, when we have only one feature, or when we have only one variable X in X that is changing, then we call it as a normal linear regression. But when we have multiple variables inside X, let's say in when we have only one feature, then it is like a column vector or a row vector where the values are changing, and correspondingly we have Y values. Now, when we are talking about having more than one feature, that is X is like composed of x1, x2, and xn, with like all the things are varying, and as a result of these parameters or variables varying, we have a output that is varying. It can be classifier or it can be a regression. So can anyone tell me what is the difference between regression and classification? I think we probably discussed this in the last class. So if some of you are shy to speak and you want to type it in the chat, what I will suggest is you raise your hand and then you start typing, so that I will wait for the answer. Otherwise, if there is a silence, then I'll move ahead. So I see that there is silence without any raised hand. So we'll move ahead. I will just tell what is regression. Regression is when the output or the response that we are trying to fit is a real number. It is a continuous number from like we can represent it in terms of rational number or something. And when we have classifier, then it is like it's an object or class. Maybe it is 0, 1, 2. This can be classification. No between the 0 and 1 is considered. No value between the 0 and 1 is considered. No value between 1 and 2 is considered. So this can be classification, and then we can later on assign 0 to, let's say, orange, and then 1 to apple, or and 2 to some other thing. So this is regression and classification that we discussed last time. Just recall. Okay, so when we have multiple features, we call it multivariate data, and that regression or the curve fitting that we are doing at that point is called multiple linear regression, or multivariate linear regression. Okay, so in that case, when we have let's now we know this multivariate linear regression. Let's go a little one step back. Now let's only assume that you have one x and one y. When you have fit a relationship between x and y, right? So, or you want to know what is the relationship? Is there a relationship between x and y? Is there, like, without using any linear regression or something, you want to know, is there a relationship between x and y? Do I actually need to fit the parameter, fit the linear regression? Then there are few statistical tests that we can do to identify that. And that, as mentioned in the class, is like covariance and correlation test we can do. So I will write, I don't like writing the formula, but still these things are actually something that we should know. So I will write the formula for covariance. Let me just write here nicely why we want to do this covariance. So we want to test the relation between variables. It can be, uh, you want, maybe you want to test the relation between x1 and x2, or you want to test the relation between x and y. So it can be anything, but we, to check that relation, or relatability, we use this covariance and correlation. So basically, what is the definition of this covariance? They don't, the covariance and correlation don't serve the same purpose, but still, what will be the definition of covariance? In simple terms, we should say that it is the measure of joint variability of two random variables. So if x and y are two random variables, then it is going to measure if there is a variability between these two variables. Okay, so if the formula for this covariance is, let's say, for x and y, it is xi minus x bar. That is, x bar is the mean we represent. I think you guys are pretty familiar with that. And so if we have n readings, then and we have two variables x and y, then the covariance between these two is given by this. Now, can anyone tell me what type of correlation is there, exists between x and y, if covariance of x and y is greater than 0? Yes, Heyman.
This is a positive.
This is a positive correlation.
Yeah. If it is zero, then there is no relationship, and if it is minus one, then it is a negative covariance.
Yeah, so when it is negative, it is negative correlated. So
Correct. It is minus one.
okay, that is correlation. Uh,
Covariance, right?
yeah, so we are talking about covariance. I don't think there
Uh,
is a range for covariance. Is there a range for covariance? Minus one to one. That is correlation, right?
okay. So then actually covariance is equivalent to zero should be independent,
Yes. So yeah.
and lesser than zero should be inversely correlated, right?
Yes, yes. So covariance doesn't have a range. We can see that from this particular, you know, this particular equation also, that we are dividing it by n minus 1, and we have x minus x bar. So if the values are going too far and we just keep on adding it by dividing it just by the number, there is not physically or mathematically, it doesn't make sense that it will be limited to minus 1 and 1. So that is correlation. There can be a little bit confusion, we'll clear that. So this is covariance. When it is greater than 0, then x and y are positively related, and if it is less than 0, then x and y are negatively related, and if it is 0, then they are independent. Okay, now let's come to the other parameter that we can use, that is correlation. So this is something that varies from minus 1 to 1, and the It's like the how do we define this? Easy way to define this, it's like we want to check what is the association between these two variables, how they are linearly associated. So it like let's say if just a sec. Yeah, let's say if your variable x and y, you know that there is a relation, there is a very solid relation, but that relation is not linear, then what do you think the value of this correlation will be? It will not be close to 1 or minus 1, because the correlation only cares about the linear uh, association between the two variables. Okay. Okay, so that's that. Now let's see what is the formula and how we can identify that it will be limited to minus 1 to 1. So it is denoted by small r, and the formula for this correlation is covariance of xy divided by square root of variance of x and square root of variance of y. Now, if you see, if you expand this, you will see that it is x minus x bar, y minus y bar, yi, and then n minus 1. And variance, what was the formula of variance? It is x sigma x minus x bar square divided by n minus 1. And we do the root of that, so it will be, sorry, sigma square. Basically, square root of variance is standard deviation, so we'll write the standard deviation here. Can anyone tell me what is the formula for standard deviation? That must be pretty easy, right? Or okay, or what we'll do is, maybe it is difficult to say that formula. I'll write it. You tell me whether it is correct or not. Okay. What do you guys think? Is this correct?
Yes.
Yeah. Thank you. Thank you. So this is correct. Now, what do we see here? We see that n minus 1 is inside the root, it will come out and it will get cancelled. And this square, so we can't remove this square because the square is inside this sigma. So if at all you're thinking that we can remove this square and we can keep this also out, so that is, we cannot do that because this square is inside the summation sign. So it will be, okay. Now you see, we can kind of get a intuition that there is in the numerator, there is something that is being repeated in the numerator. So the value will be in the range of minus 1 to 1, because there is no absolute here. This value can, above value can be negative also, and the bottom value will always be positive. So we can get an intuition from this formula that this value can be from minus 1 to 1, and that is true. The range of correlation is from minus 1 to 1. Square brackets indicate that the value minus 1 and 1 are included in the range. Okay, and the same thing, when covariance is less than 0, that means the r also is less than 0. And let's write it like this: when r belongs to minus 1 to 0, so minus 1 included and 0 excluded, we have a negative relationship. And when r is equal to minus 1, we have a strongly linear negative relationship. We should write it as strongly negative linear relationship. When r is equal to plus 1, we have strongly positive linear relationship. And similarly, like this range, we will have the range for excluding 0 to 1, that is for positive relationship. And what if r is equal to 0? That means our covariance is 0. we can say that numerator is 0, then there is no relationship. Okay, so this there is a statement that can come as an MCQ in your exam. I am going to write the question here, and I want you guys to put the answer as yes or no in the chat. So calculation of correlation is insensitive to outliers. So now you guys write in the chat your answer, whether it is true or false. You can just T or F, you can type. What do you guys think? I think it was one of the points in PPT. So we are just trying to recall what we have learned. No one? Let me check the chat. So okay, so no one has responded yet. I don't think that it is a tough question, but still, if and so the answer for this is false. So correlation value that you have calculating using this formula is very sensitive to outliers. So if you have x and y nicely, a very nice linear relationship, right? And you have an outlier. What is an out? Okay, so what is an outlier? Maybe it was not clear what I meant by outlier.
I think the variable that goes out of the linear scatter chart.
Yeah, so that is visually from a visual inspection, you can say outlier are like that. And defining outlier, if you want to understand what is actually meaning by what we actually mean by outlier when we say, so it is like when any response or any reading, any data that is statistically very different from the other data in the same group. So now we see here x and y are nicely varying in this straight line. So we can say, okay, so these are this is maybe let's say 1:1 line, and we can say x is equal to 1 is the probable relation from visual inspection. But some person, or maybe the person who was performing experiment, made a mistake in one of the procedures at any given point, and for that there is a response, that is why you are obtaining, that is very far from what is generally observed. So these things that are that are outside your general behavior, that show a very different statistical behavior that than the other observed values, they are called classic like outliers. So this is like the general kind of conceptual definition of outliers. Okay, so now the answer to this question, calculation of correlation, sorry, let me write, calculation of correlation is insensitive to outliers. It means this question is saying that if you, even if you have outliers, this correlation value is not going to change. And for this example, it is going to say that x and y are very nicely correlated, and it is going to say, for this example we can see it is positive. So it you may think that it will say that there is a correlation value, that is the, sorry, that is the small r is equal to 0.99. But that is not going to be the case, because we have outliers here. So it will be less than this 0.199, it will be 0.85 or zero point 0.8. So it will decrease because of these outliers. Okay, so one thing to note. Okay, so in this course, actually, some terminologies will be followed. That is, let me state those terminologies. That is, when you are fitting a data, that's the output, it will be called response dependent variable and endogenous variable. So response and dependent variable you can remember, but let me write here endogenous variable. And the input, that is your independent variable, it will be called as explanatory variable, independent variable, exogenous variable, or predictor. So here this term exogenous variable I will mention. So this is going to be your, sorry, output, and this is going to be your input. So just a few things to remember by. Okay, now so we have defined outliers, and let's see what else was there in this. So yeah, now let's come to the simple linear regression. How you, so not many people have joined today, but how many of you have an idea of simple linear regression, or is it completely new for you? So I would like the person for whom it is new to respond. Yes, Hemant wants to say something. So yes, Mr. Hemant, is it new for you? I am new. Okay, good, good.
Yes, I'm new.
Okay. So now let's go to the simple linear regression. Oh, sorry. SLR. Let's write it in the short form. Okay. So what does regression do? Now regression tries to find out. Okay. Is did you want to ask anything else, Mr. Hemant?
No, no, no. Actually, I'm just listening.
Okay, okay, okay.
Go ahead, please.
Okay. So I lower the hand. I forgot to lower the hand. I thought you raised it again. Okay. Yeah, so what this basically regression does. So regression generally identifies one independent variable and another dependent variable, and how this independent variable is actually impacting the dependent variable. So we have seen that we are going to, for this course, we are going to depict our x as an independent variable and y as the dependent variable. So regression tries to find how the change in x is going to change in y. Simple linear regression. So we are talking about simple linear regression. Linearity means there is no power and there is no other kind of gibberish in the term. It is simple linear equation that we have seen y equal to mx plus c line, one line equation. Similarly, here it will be b y is equal to beta naught plus beta 1 x. These two are the parameters that simple linear regression tries to estimate given the data. Okay, so what is B naught? B naught is the inherent property, you can say, for the dependent variable, and the important thing is B1. B1 represents the change in rate of change of y per unit change of x. So if it is only single variable, then it is going to represent the rate of change of y per unit rate of change of x. Now, but let's say if you have multivariable regression, multivariate regression, so it will be b naught plus b1 plus b2 plus so on. So in that case, how do you define b1? The definition of b1 will change. Previously, definition of B1 is the rate of change of y per unit change in x. Now the definition of B1 will be the rate of change of y per unit change in x1 given other variables are constant, because these variables can also change and together they can have a different impact on y, but we want only the we want to study only the impact of x1 on y. So that's how the definition is going to change slightly. So that will multivariate we'll see in the later sessions. We'll see the simple linear regression now. Okay, so what are the assumptions of this simple linear regression? When we are trying to fit a simple linear line model to our data, what we will definitely make some assumptions, because nothing is very smooth, very linear in real world. So we have to make certain assumptions. So let me make some rough data. So we are trying to give this. Okay, this is, let's say, our scatter plot, and we see that there is a relation, linear relation. Now we will try to fit it. So let's say this is our fitted line. Fitted line. Now, what actually we tried to fit? See, we had so many data, but and we had x, for x we had here this value. Let's say we have x1, and yeah, let's say we had this x1. It can be confusing, so I'll say this is the one value of x1, the x, this is second value of x. So we have so many values of y for these x. But you see this fitted line, this is not telling us these values exactly, it is telling some kind of average value. So what we should understand here is, when we are fitting a simple linear regression, we are going to fit regression or the model for the mean of the observation. So here in this x, let's say we have an x naught here. So we have a spread of y. Now we are going to identify one mean. We are going to fit the mean. So how will it look like? How will the distribution look like? It will look like something like this. For different value, maybe drawing it more clearly, it will look something like this. So the value that is in the center of this data, we are trying to fit that. How will we write this? We will write this as new. From our school we have understand that when we write this symbol, that is mu, we are talking about mean. So here also we will write mu y, that is mean of y. We are going to predict it is going to be b naught plus b1 x. This line we are going to predict. Okay, then this is fine. Then what about the actual spread of the data? For that we are going to use something called error. So it is going to give us the range of this data. So actual y is going to look like mu y plus error. So this is the mean. Uh, let's say this fitted line is actually, forget about the fitting here. Let's say this is the mean line. The green line is the mean line, and these are the errors which actually is depicting the spread of this data that we have. So we will try to fit this mean and have an error to represent the spread of this data. So what is the assumption? Now let's come to the assumption. One of the assumptions of this simple linear regression is that this error that we are talking about here across the mean for this observation is going to follow a normal distribution. So simple words, we will write error. We are saying this error, but more commonly or more accurately we should call this as the variance of this data, variance of this spread. So we are going to say this error is following a normal distribution. And what properties does the normal distribution has? It has its mean, and it has its standard deviation and or variance. So this error will have zero mean, and the standard deviation or the variance of sigma square, which is going to be constant for all the x values, because error here can be different. Error for this x can be different for the from the error for this x. So we are assuming that this error is going to follow a same trend no matter where in the observation line we are located. So these are the two. So this is one. that it is going to follow a normal distribution, and the second is the mean, it will be 0, and variance will be sigma square, which will be constant. So these are the two assumptions. But what other assumption is? Another assumption is we are going to fit a linear regression. We are going to fit a line equation here. So that means that we are assuming that so the relation is linear. So this is another assumption, related linearly. Okay, what is the fourth assumption? So this may be a little bit, this assumptions, the importance of this assumption may not be clear now, but still we'll state this assumption. So this assumption states that this observation at x1, sorry, see this observation at x1 is independent of the observation at x2. So let's understand. So we'll write this first. Observations or the response experiments, let's call them experiments or observations, are independent. So let's understand this. Now, I want to do an experiment, or I want to know how many blows, how many hits from the X. I want to know how many hits from the X does an average person with age, with increasing age, what is the trend of the number of hits an average person will take to cut a tree trunk. So this tree, I want to know the trend. So basically, as the person's age increases, let's say I'm starting from age of 30. So it's a peak age. Let's consider that. And from 30, we will see that when the person gets older, there will be an increasing number of hits. So they will get weaker and weaker. So the number of hits that they will require will increase. Now I want to do this. In order to do this experiment, I need similar uh, similar kind of trunk, and I should use one person only one time, right? So how this fourth assumption is going to be violated, let's see. I'm trying to explain this fourth assumption using this example. Let's say I one very weak 30-year-old person, I gave him a log of wood or the trunk, and I asked him to cut this. Now he is not able to do that. There is a, let's say we put a threshold that after this many hits or thing, you are disqualified. So he is not able to break that trunk. Now I cannot give this trunk to any other participant, because in this trunk has been physically damaged, not completely but somewhat damaged. So if I give this to another participant, let's say to an age of 35, he may be able to break this trunk in less number of hits. So what it will do, it is going to increase, it is going to show that his strength is more, and it is going to shift the point here. So what is happening here? There is kind of a dependability of the input that I have, because there was one person in who took more number of hits, but he was not able to break. So that person may be located here, but this person used the same log, and he was able to break this log or trunk in less number of time. So it's kind of, we have a dependability between these variables. So we cannot have that when we are trying to perform a linear regression. This is just an example to show, to explain that how this kind of dependability in the variables can arise. We have to avoid that when we are taking the readings, and if we want to fit any kind of simple linear regression model in the future. Okay, so this was clear that when we are performing simple linear regression, we are trying to fit this mean of the observation, and the y actual prediction or the range is denoted by this. Now this error, we said that it is going to follow a normal distribution with mean 0 and variance sigma square. So we can just replace this by sigma square. Now I have a question for you guys. Is can I write? So this means that there is a mean of 0 and variance of sigma square. Okay. Now can I write this as, sorry, can I write y from above expression as this? I just want yes or no. So someone has put a message in the chat. Okay. 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 It's the old message. Yes. So yes or no. Then I will explain what is the correct answer and whether we can write it or not. Like that. Okay. So no one wants to give it a shot. So we can actually write it. Now, what does this mean when we say this? When we are adding a constant term to a normal distribution, what is happening? The mean of that normal distribution is increased by the same amount as the constant, but the variance is same. Now, understand this mathematically, that what you are doing when you are adding, let's say this is your normal distribution, which means 0. These are all values. So what you are doing is, if you are adding a constant value to this normal distribution, that means you are adding a value to all these points. So it's like shifting the normal distribution. So this normal distribution didn't change, but it just got shifted from zero mean to new y with the same spread. When the spread is same, the variability is not going to change. The variance is not going to change. So we can write this as this equation. Sorry, this particular equation in this short form. And since we are estimating, no, we are going to use simple linear regression to do the estimation. So this ends up being written as this. Okay, now let's see. So sir didn't discuss about how to get this B naught and B1, which is something I think you should know, since if you are new to this linear regression, this will give you a kind of confidence boost that I have mastered this linear regression. Now we will do the then we can handle the non-linear regression or multivariate regression also. So now let's try to get those equations that sir showed in the class for B naught and B1. How do we actually get those equations? So the one important thing is the equation that I will be deriving or getting. It is a simpler form of that equation. So the equation showed by sir, that is also correct. The equation that I am going to derive, that is also correct. You can simplify the equation that sir showed in class, and you will get the equation that I am going to show or derive in this session. Okay, so what does it mean? So before we go to the derivation of those parameters, I want to know, or I want to explain, what does it mean when we say we have fit a linear line for a, for this given set of data. So it means that you have this data. Let's say you have this data. Now I have fit a line that is the best fit line for to explain the behavior of y with x given this data. So that means I have fit this line. Now why this line is best, or how do we judge that this line is best, is actually using the sum of square errors that sir discussed in the class. So we have different values of x and correspondingly we have different values of y, and from our prediction, so this is our prediction line. From our prediction line we can get some value for that, we can get some value for that this x, but this actual value for the of y is this, we from our prediction we are getting this value. So this is the error, so this is the error for this reading. Similarly, if you talk about this x, this is the value of y we are getting, but this is the actual value. So again we have an error this. So this is the line is called best fit line when you have the parameters b1 b0 and b1 such that the sum of the squared errors is minimum. Then you say that this line is the best line. Now there is a huge controversy, uh, not let's say debate. Yeah, better word would be debate. So within the people in the community, some people like to say that we are not actually. Let me make it here itself. We are not actually minimizing, yeah, we are not actually minimizing this vertical distance, rather we are minimizing the perpendicular distance. So my question to you guys is, using simple math and concept, given that this predicted line will be, sorry, given that the predicted line will be always constant, is given to us, you tell me, will there be a difference between the two approaches? Will there be a difference between the parameters if we are only trying to get the b0 and b1? Will there be any difference in the parameters that we obtain if we are going to use not this vertical distance but the perpendicular distance? So I will give you a hint. I will give you a hint. So what is this sum of square errors? Even though sir has told, but I will write this. It is going to be the sum of y predicted minus y actual, and then you square this. This is the sum of square error. Now this yi hat minus yi is the vertical. Now I say no, I don't want to do this vertical. Actually, the distance, the more representative form will be if I take the perpendicular distance of the point from the line, and I want to use that to fit my best line. So do you guys think there will be any difference between the uh, beta naught and beta 1 that we are going to get? Use trigonometry and tell me. So one more hint I will give you, that first hint is I have given that use trigonometry. Now one more hint I am going to tell you, that if you know the hypotenuse of a triangle and the angle of that triangle and this angle, let's say this angle or this angle, you know this, you can get this. You can get the base and you can get the height. Let's call this B1 and let's call this B2. Now you just think a little bit. Will there be a difference between the parameters? If you know the answer and you don't know the explanation, that also will work. Okay, we'll not spend more time on that. So the answer is there will be no difference in the parameters. Why is that? See, we know this distance. Can we know? Can we identify this distance from this vertical distance? Yes, we can identify. Let's say I know this angle. Let's say I know this. Let me highlight this particular angle. And then what will be the What perpendicular distance, it is just going to be vertical distance, that is this into cos theta, right? And then we do the square of this. This is going to be the vertical thing. Now one thing to note here is the slope of this line. Considering one line, linear regression, the slope of this line is not going to change. So when the slope of this line is not going to change, that means this angle, this particular angle is not going to change. Now I want an answer, yes or no. If this angle is not going to change, can you tell me, is this angle going to change? What do you think? If anyone, raise your hand. If do you think you can answer this? If I am not changing the angle of the line, do you think the angle of the this particular angle that we have highlighted now with the green, with the like blue, yellow, green, that this is going to change? Now it is blue. It is not going to change, right? Anyone has any contradictory response? Then we can discuss. Okay, so I believe that everyone understood this. So this, when this angle is not going to change, that means this cos theta is going to be constant, right? Now when cos theta is constant, and then we can just take this expression out, and when we are minimizing this, we don't even need to worry about cos theta. We can minimize this particular expression, and the whole thing is going to be minimized. Isn't it true? So that is why no matter what approach you take, your response is not going to change. Okay, now let's go to the derivation, actual derivation that everyone is waiting for. Okay, so what is this error? SSE is the sum of square error. Sum of square error. How do we write this prediction? We write this prediction beta naught hat plus beta 1 hat xi minus yi square. Now we want beta naught hat and beta 1 hat such that this is minimum. So what is the way to do this? How do we identify this? We have to, so anyone wants to take a shot? How do we get the minimum of a function? So this is going to be a function. Let's say this is fx. Now I want to find, don't forget about two variables. Just you have one variable fx and the function fx. Now I want to find the minimum or maximum for this function. What is the usual approach that anyone follows to get this? So the approach is, you identify the stationary point, making the f dash x is equal to 0, and then you check using the double differential if it is less than 0 or greater than 0, whether it is minimum or maximum. If it is greater than 0, minimum; less than 0, maximum. But in our case, we have formulated our cost function or the function's sum of square error in such a way that it is going to be minimum only. So what we need to do is just we need to get the differentiation with respect to b naught and b naught hat and b1 hat, and then put it to 0. Then we are good to go. We will have the answer. Okay, now let's try to differentiate this. I will just say this as s for now. Okay, now let's differentiate this with respect to B naught. So sigma will keep aside. Now let's differentiate this. The differentiation. So if you have any doubt for the differentiation, I will suggest you to refer to the basic texts, our undergraduate or graduate level books to understand how the differentiation works. I'm just going to differentiate this and show it to you. So this is going to be 2. The power will come here, and this is going to be b naught plus even x1 minus yi, and then plus 1 when we differentiate this b naught hat separately. Now this expression we have to put to 0. Okay, then we expand this, we give the sigma to every constant, and we just delete this 2, because 2 can go to the right side and plus 1 can go to the right side, and they all can vanish in the 0. Now we have okay, so b naught hat is constant, so this is our b naught hat sigma 1 1 to n, and then b1 hat sigma xi 1 to n, and then minus sigma yi 1 to n. What will be the answer when we add 1 n number of times? It is n. So this, whenever you have a sigma I is equal to 1 and to any number, let's say m, and then you have a constant here, what this means is you have to add this constant m number of times. So it is just going to be km. Similarly, in this case, it is going to be n beta naught hat. And what does this look like? So if you remember how we wrote mean, it is I equal to 1 to n xi divided by n. So we have something, we have the numerator of that expression on this here. So we can write this as beta 1 hat x bar into n. And similarly, we can write for yi, sigma yi, as y bar into n. Now do we know beta naught now? Yes, we can cancel out the n, and beta naught simply comes out to be y bar minus beta 1 x bar as the answer for beta naught. But here's the catch: beta naught is dependent on beta 1. So we need to find both of them, and then only we'll be able to get the answer. Okay, so let's try to find beta 1. For that, we have to differentiate this expression with beta 1 hat also. Okay, so let me keep it here and let's try to differentiate. First of all, we'll keep the sigma psi, and the first term will be the same. And now when we differentiate separately this inner term with the beta 1, we will get xi. This has to go to 0. Keeping so all these places sigma will be there. I'm just not going to write it every time. So, and then this 2 can go to this 0. Now let's multiply these two together. So we have beta naught xi plus, or maybe I'll write the sigma, otherwise it can be confusing for some people. Beta naught xi plus beta 1 hat xi square minus yi xi. Now let's expand this beta naught hat. We see this beta naught hat here. Now let's put the value of beta naught hat from this expression into this expression. So other things are going to remain same. Now let's expand this also. Now you will see that we have only beta 1 here and then 0 here, so we can shift some quantities to the right side and we can get the expression for beta 1 hat. Let's try to get that. Now let's give sigma to everyone. Now this y bar is the mean of y. It is a constant, so it will come out. So we will get this. Similarly, beta 1 hat and x bar, these both are constant. They will come out, and xi will get the sigma, and here also xi square will get the sigma, and this is simply sigma xi yi is equal to 0. Now when you simplify this, you are going to get the expression for beta naught as sigma yi xi minus y bar sigma xi divided by sigma xi square minus beta beta we have to, yeah, x bar and sigma xi. This expression we can leave it at this. This is the answer for beta 1 hat. But to make this little easy on the eyes and easy to understand, let's again use this mean concept, the mean formula, to simplify this expression. Now whenever I have written here sigma, this sigma is from 1 to n. So this thing, sigma xi, can be written as x bar into n. Here also sigma xi can be written as x bar into n. So let's actually do that. Sigma yi xi minus y bar x bar divided by sigma xi square minus n x bar square. So this actually looks, sorry, this here also n will be there. So this looks a little bit pleasing. Or if you want to write it a little bit more nicely, then you can write it like this. Because maybe this is more easier to remember. Now, whichever suits you, you can use that format. So is that clear to everyone how we are getting the beta 1 hat and beta naught hat? Because see, the formula that sir has given, it is also accurate, 100% accurate, but you can simplify that to get to this, or you can add and subtract variables from this formula to get to that. That is something that is not very important, so I'll be not covering that, but I just wanted to show you that you can get beta naught hat and beta 1 hat using these steps. Now you similarly, this is what we have done. This is we have done for a simple linear regression, like for only one variable. Even if there are more variables, you can follow the same step and get the expression of for beta 2 hat also. Okay, so it's like now you can, if you spend time, you can actually, you don't have to use Excel or machine. You can manually also calculate the parameters for beta naught hat and beta 1 hat, and even if you have more variables, you can go for multivariable uh, linear regression also, multivariate linear regression. Okay, so this is for the simple linear regression. Now I want to ask you guys from this PPT, it is, this topic is this particular point is not extremely important, but it is so good conceptually that I felt like I should discuss this. See, if you have a line that you have fitted, this is your fitted line, and these are your points. Okay, now we see that these points are increasing, they are following some trend. So with x, y is following some trend. Is it correct? Yes. So we can see that from y is following some trend based on x. Now what do we predict? We predict the trend followed by mean. We predict the trend that mean follows. So if let's say we say that y doesn't vary from with x, and y has only one value, then what value that will be? It will be the mean of all the values of y. All these y here, you take them, you take the mean of these things, and you say that y doesn't follow any trend. This will be that line. So without any adjustment, you just take the mean of all the values. This is going to be that line. And it is saying that y is not following any trend the with x. Our model is able to explain that y is following a trend with this variable x. So which error is our model able to explain? If there is an error, which error is our model able to explain? So consider this point. Let me highlight this. Consider this point. Our model is able to explain this error. So if there was no trend, it will be just simply y bar, but there is a trend and our model is able to explain this. So this is the error that our model is able to explain. That see, there is a trend for the y with respect to x. But the actual error, that is this total, it is not explained by the model. There is this part of this actual error is not explained by the model. Because if you remember, this is only the sum of square error that we tried to minimize in our curve fitting or our linear regression model. So whatever is remaining is something that our model not able to explain. So what do we say? So you have to so the total error is something that our model is able to explain, plus our model not able to explain. What is the error that is not able to explain? This is the error that we have tried to minimize through this equation, that is sum of square error. So sum of square error, and the error which our model not able to explain, that is the sum square regression. Okay, so it is so we can actually, if you are given these two things, you can get the value of r square. I don't think it is going to be asked because it is pretty simple, but this is the formula for that r square. In that case, it is if this kind of problem will come, even if it comes, it is going to be purely conceptual problem. So I wanted to share with you guys this particular concept, that our model is not able to explain the error, and that is the error that we are trying to minimize through our linear regression. Okay, so this simple linear regression is done. Let's go to the other part, that was confidence interval and prediction interval. So from the lecture notes, who is able to understand the confidence interval and prediction interval? So let me draw the plot. So you have y, you have x, you have lot of data. Here is the data distributed. Now this is the mean prediction, and this is some interval. This is another interval. So what is this orange, and what is this green? So I am asking for the confidence interval and prediction interval. What is this orange and what is this green? See, we are not going to discuss here the formulas for calculating this confidence interval and prediction interval, because they will change based on the method you want to calculate them with. And when it comes to, when we are going to anyhow discuss these things in probably in the future sessions when we have some actual data, so we'll not worry about those things now. But I want to know, what do you guys think is the confidence interval, and what is the which represents the prediction interval? Okay, so still no hand. So the confidence interval refers to the range of values that is acceptable for the mean of the observation. So if your model is going to predict the mean, then your mean can lie within this range. And the confidence interval is basically usually defined it as 95%, 99%, and all those things, so that you will have you will read in the probability statistics. So that based on that, though that particular confidence interval, you will get a range of maximum and minimum y value or minimum value that that your model will give uh, mean inside that range. So if your model is giving inside that range the mean value, then we will say that yes, it is no, it is a good model. And if it is giving outside that, it is no, it is not usually considered good for the statistical analysis. So let me write here. I will, so that you remember, I am going to remove this color, keeping the orange and green. Yeah, so orange is confidence interval and green is prediction interval. Okay. Now, what does confidence interval tell us? It gives us the preferred range of values of mean of the distribution. And what does prediction interval tell us? Prediction interval actually tries to encompass or tries to make a bound for all the statistically relevant observations. So you will not be wrong to think that this prediction interval is going to ignore the outliers. Okay. So what is prediction interval? So it is going to give the range of estimate of y, the observation, for any x. So these are not bookish definitions. These are just definitions that so that you can understand the basic principle what is going on here. Okay, and if you so the formulas I am not discussing because it is just going to eat the time. It is and it is not also derivational, it is just a mugging up of the formula, so you can do that on your own. Okay, now what else is there? So after that, it was in the class we discussed the diagnosis of problems. So we had made certain assumptions in our simple linear regression, right? Now, how to identify that whether these assumptions are valid or not? So what we had made the what assumption we had made was this residuals. Also, we termed it as error. So we have fit a model, and this is the predicted value. This is the actual value. Sorry, this is the actual value. This is the residual. Let's let's not give it any r or anything. Otherwise, it can be confused with the correlation. So this is the residual, that is y my I minus y hat, that is the prediction. So this is going to be uniform. We made this assumption. It is going to be uniform, and it is not going to vary with very much with x, with x. So our value or our expression doesn't look like this. The spread of points is fairly uniform across the x. It is not going, like, it's not spreading as we go along the x. So I'm going to draw 4 plots, and based on the plots that you have seen in the class, I want the answer that which plot shows a good uniformity and non-dependence of residual on the observation, that is the x. So I'm going to draw 4 plots here, and I wish and I hope that you will participate by telling me the answer. So this is residual. Let's just write res, and this is x. So which plot do you think is showing that the residual is uniform and non-dependent on the observation x? Is it A? Is it B? C? Is it D? Come on, guys. What do you guys think? Give it a shot. So the residual, you remember, residual has to be uniform and it has to not depend on x. B. So correctly, Kuruvin Shetty, if I'm sorry if I'm pronouncing your name wrong, so has given the correct answer, that is B. So you should not you should not be fooled by me using the different kind of lines into this. See, easily you can identify that only in this plot residual is not dependent on x because it is flat, whereas in this it is increasing and becoming saturated with x in this plot, and in this plot it is decreasing and becoming saturated with x, and in this plot it is just continuously increasing with x. So only the figure b is a good representation of the residual being uniform and non-dependent on the observation. Now we also made one assumption, and that was this spread of the spread of the observation or the response across this particular x is uh, is normally distributed. So that and there is a and now I will ask you which figure actually is showing that this residual is normally distributed. So if you notice, so I will, after this question I will say what I had done for the A, B, C and D. This normal quartile. So if you have gone through the class sincerely, then you will be able to tell me which one, and this is residual again, and probably this was in your assignment also, and you have the answer for that. So if you have analyzed your assignments, then you should be able to tell me which plot is showing that the normal distribution of residuals are normally distributed. It is not right skewed, it is not rest skewed. Okay, very good. So again, Purvin Shetty has rightly told that it is B. So I think only Kurvin Shetty has read and sincerely gone through the PPTs. So B is the correct answer. If you guys have doubt, then you can ask Kurvin Shetty or you can refer to the PPT because this is pretty straightforward. This is the this is correct one. This is showing the normal distribution, and these plots are just not significant because I just drew gibberish here. I wanted to confuse you guys, so I swapped the PPT figures with these two, and still Kurvan Shetty was able to figure it out. So that's a good thing. Now comes the part that was not that is going to be important in the future. It is now we are actually going into the complexity of actual machine learning and data processing. Okay, so when we have let's talk about this multivariate linear regression. So that means we have more variables, more features, let's say n features, but still we want to fit a linear response to y. Okay, so in that case, what we have to account for, one main problem that can that if we solve that, it can save us some resources and computational cost, is the multicollinearity. What is multicollinearity? So when a feature is dependent on another feature or a set of features, then we call this as multicollinearity, linearly dependent in this particular case. So so as you know, I also discussed in week 1 that when we are doing feature selection, then we saw that the feature which is redundant, we should remove it because it is not going to give any new information, and it is just bringing more cost to our regression. So this multicollinearity is going to be a problem when we are talking about multivariate linear regression, because as sir discussed in the class, that it can be that you have one of the parameters as weight and another parameter as BIM, and you can have temperature in degree centigrade and Fahrenheit. So there is no new information given by these two sets of parameters. So they are giving the body health of the person and the temperature. So we don't need to have both of these things together. Okay, so how do we avoid that? To avoid that, we read that we should use BIF, that is variance inflation factor. So this was not 100% explained as to how we have to go about doing this. So let me just take 2 minutes to explain this. So the formula for VIF was given in the class. It is 1 by 1 minus r square. But how do you calculate this? So to do this, you should follow these steps. So let's say you have n number of features, n number of variables, and you have one output, that is y, and these are all stored in the x matrix. Now what you do is you forget about this output first of all. Forget about this dependent variable. Only look at these independent variable because we are trying to find out the multicollinearity between them. So these are not the steps to write in the book, but I will write it for the general purpose, that is forget about y, that is the dependent variable. Then what you do, one by one, take a feature. Let's say I take x1 and consider this as the dependent variable. Okay, so you had n features. What you do, you consider x1 now as dependent variable and x2 to xn as independent variable, and now you fit your linear regression. And when you do that, after doing that, you calculate the r square for that. So how should we do this? Let's say you have x1, x2, x3 and y. You forget about y and you see what is the best line that you can fit in this 3D space that describes how x1 is dependent on x2 and x3. So let's say this is that 3D line, and let's say that we get a very good r square value. So that means these x2 and x3 can explain the variability in x1 very nicely. That means x1 is not going to give us any new data, any new information. So if the r square is high, that means this VIF is going to be high, and that means x1 is strongly correlated to the other independent data, or let's not call them independent yet, other features. And if that is the case, then you don't consider or you remove x1 from your analysis. And if you are getting confused, let me just write x is this, x1 is this feature, x2 is this feature, x3 is this feature. Okay, so x1 is a feature which is varying. So for different data set, different point, x1 is different point, x1 is different. So it is a vector, it is not a single value. Okay, so we know that r square range is from 0 to 1. What is the range for VIF given the formula is this? Okay, so no one wants to say 1 to 100. So minimum is right, maximum is actually infinity, and we can see that when 1 to infinity, yes, correct again. So when r is 0, r square is 0, then you will see that it is 1 minus 0, that is 1 is the minimum. Now when r is 1, It is going to be 1 1 minus 1. So actually this is not defined, but let's assume an r value that is very close to 1, 0.9999999. So then on the denominator it will be 0.00000001. Now when this goes up, then it will be 10 to power 7, right? So it is much more than 100. The maximum value is actually till infinity. So the range of VIF is 1 to infinity, infinity excluded. Okay, so that is the range of VIF. So what you do, you have set of features, right? You have x1, x2, x3, x4. What you first put x1 as an dependent variable, you calculate the VIF. Then you put x2 as an, and when you do x2 as a dependent variable, you have to again consider x1 as a, independent variable. Then you compute this thing VIF for x2, and similarly you keep on doing that, and then you remove whatever variable or feature is having the highest x1. If all are having highest VIF, if all are having similar VIF, let's say around less than 5, then no need to it seems that everything is independent and no need to remove any of the data. Okay, so that is how we go about dealing with the multicollinearity. So this is one of the problems with the linear regression that we can encounter, multiple linear regression. What can be another problem that was discussed very thoroughly, and uh, time over time sir has mentioned this? What do you think is another problem? It is overfitting. So we have overfitting as another problem. Overfitting and underfitting. So I have two simple figures to explain. If you have doubt, if you are having trouble that with the points that overfitting is having will have less bias and high variance, let me try to explain this. So what is basically overfitting? So you have this figure, and you have simple data. Let's consider simple data. It is showing y with x. These are your observation points. Overfitting is when you train your model such that it will capture even the small errors or small mistakes in your reading. Like it will capture the smallest features that are there to in the reading. It will capture. So the uh, the most overfitted model for this set of data will look like this. It is passing through all the points. This will be the overfitted model. And what will be the underfit model? Underfit model can be anything. One of the example for underfit model can be this. Oh, sorry, that it doesn't even see the trend between x and y and x, and it is just this. So this is underfit, and this is overfit. A good model. What is a good model? A good model is something that will capture the trend, but will have certain errors in that also. Now, when we say that the overfit model has a less bias, so what do we mean by this bias? So in the definition, it was discussed that bias is the error that the model introduces when it is trying to replicate any real process, right? So how do we quantify the bias? If you want to visually quantify the bias, you just look at the difference. Now again, this is not the book's definition, this is just so that you can understand the concept of bias. If you want to quantify or visualize, you just see the difference between the observation and the prediction. So what do we see here? This underfit model is having very high difference between the observation and prediction, right? So it is having high bias. We'll come to the variance. Let's talk about the bias for the overfit. You see here that the overfit model doesn't show much difference between the prediction and the simulated value, because it is passing through all the points. So it is having low bias. Okay, now, and this good model, it has some biases and some variance. So this there exists some difference for the good model, right? So it is having some bias, but it is not too much. Okay, now what about variance? How do you define variance? Variance is, to explain variance is to understand what variance is conceptually. You should see how much the estimation, how much this line that we have fit, it is going to change if we have different training data but for the same relationship. Like, we want to capture the same trend, but if I give it different training data, how much is the estimate going to change? So it is a measure of how much the estimation going to change if we give different training data, if training data is changed. Okay, so let's me draw same trend I want to capture between y and x, but instead of very closely spaced x data, now let me give very sparse x data. Now what do you think the overfit model will look like? Overfit model now is going to look like this, right? It is going to capture everything, and it is just one of the overfit models. See, when we try to fit overfit models in our, when I am doing personally some experiments, we will see that when there is a huge difference between the x values, it will just do some funny things in between and then come back to this point, and then again some funny thing and then come back to this point. So that can happen. I'm just drawing the simplest overfit model here. Overfit models can also be complex. They are complex actually. That's their nature, but they can increase in complexity. Now, how about the underfit? That was just the y bar that said there is no trend. It is the same, or more or less the same. Then how about the good one? So the good one will be set good if, okay, if it is not changing much with the change in the data. So let's say it changed a little bit, but it didn't change that much. So what do we see here? When we said variance is how much the estimate is going to change, it changed a lot for this overfit model. It was like a very nice wave. Now it is a high wavelength wave. So it is having high variance. And what about this underfit model? It is having low variance, because we don't see much change between this y bar and this y bar, right? And the good model is a model which have the bias and variance both in a balanced kind of way. So that is what the equation for the error, it was shown that irremovable error and then plus bias square plus variance. So this is the error that is probably some of the models they use when they are trying to fit any kind of linear regression to the given set of data. Okay, so now I have, so this is the overfitting and underfitting, and I'm not going to repeat. So because sir showed it so many times to, so that you guys can understand, I'm not going to do the same thing. So you just remember that whenever the model complexity increases, it is going to be overfitted, it is going to have less bias but more variance. Whereas if the it is underfitted, it is simpler model, it is not going to have much bias, but it is going to be having sorry, it is going to have more bias, but it is not going to have much variance. Okay, coming to now only few more points that are important. One of the very important points, that you will come across in machine learning, probably not in not in soil, or maybe in soil we'll see, is the KNN. That is the K nearest neighbor. So this is a classification methodology that is used when we want to classify some set of points, some set of data. What does this mean actually? What is the basic principle behind this? So first of all, this is a classifier, and it does the classification of any point not only based on the nature of that point, but also based on the nature of its neighbors. And how many neighbors? K neighbors. So you can change the value of k. So it classifies the data, just defining it in terms of layman, classify the data point based on k nearest neighbor. Okay, and this k nearest neighbor, the k like it will include that point itself. So if I am saying k is equal to 1, it is only going to look at itself. Okay, so what does this signify? Let's say I have bunch of green points arranged, and I have a red point in between. Now if I use k nearest neighbor and I say set the value of k as 4 or anything greater than 2, what it will do, it is going to go and see that this is the point, that is, these are the 2 points, and so we have chosen 4, and this is the third point that is nearest to this, and along with its own property it is going to check their property. And when it does that, it will get an output something like green, 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 red, and it is going to decide based on majority and classify this red point as green point. So now if I want to see the region for green, I will see this whole thing as the green region, which is not accurate, but it is simple, right? Now if I have, like, I'm just trying to explain the concept here. We'll talk about the We have already talked about the overfitting and underfitting. I'll just mention it in the end. Now if I say that k value is 1, then what do you think will be the classification now? How will it classify this point? Red or green? R or G? Okay, so you can type it in the chat box. R or G, just one letter. Okay, so it is going to classify it as a red point only, because it doesn't care now about the other side neighbors. What happens if k is equal to 2? When k is equal to 2, its own input is going to tell it that it is red, and the other input that it is going to get from the neighbor, it is going to tell that it is green. Then it's a case of what kind of activation function, or what kind of let's say a main function you are using. Are you just, if in the 50-50 case, some people like to use yeah, sigmoid. Sigmoid, I don't know whether it will be useful here, but some people like to use just randomness. So because sigmoid in this case also I think is going to give the same answer for both, because they both are in the same number. Some people try to use randomness. It's like it's just based on the model itself, whether it is going to give red or green, just based on the code that you have written. Okay, so that is, we need to give odd. So Kurvin Shetty has put a message. We need to give odd values, so probability prediction will be good. Okay, so we can give odd values as said. So we can give the k not as 2, but we can give k as 3 and 5, so that there is no tie. So that's a good point that Kurvin Shetty has mentioned. So we can give the k value as odd, so that we can completely avoid this kind of problem. Nice. Okay, so this is k nearest neighbor classification. Now, when we give k value as very high, that is, let's say 100, then it is going to generalize that area. Then it is going to check all the 100 neighbors, and then it is going to classify that area into red or green. So in this particular case, uh, it is going to classify this area as green. But when we give k value as low, let's say 1, then how will the classification look like? The classification of the area, it is going to classify this as red. Actually, this is good. This will be a good classification, but rather when you give k is equal to 1, it is going to classify something like this, and then this. So which is not good actually. So there will be a trade-off that you can, that we can get through the code, or with our trial and error, which is going to give us the k for the classification boundary as this for the red. And now my question, since sir mentioned it so many times, I want to ask you guys now. When k is high, when the model is very general model, general basic model, what will be high? Bias? Sorry, bias or variance? Uh, think again. Try again. Kurvin Shetty, what we learned from overfitting? We learned that a very simple model is not going to change much with the different training data, and a simple model always has more bias and less variance. Simple model doesn't overfit, right? So a model which doesn't overfit, what will it have? It will have high bias. Is it clear? If you think I'm saying wrong, that you can tell me that also. I can also go back and check. So if it is clear, then you can tell me. Okay, okay, good. Thank you. So k is equal to 100, which is going to be very general model, will have high bias but low variance. Whereas k is equal to when it 1, it will be overfit, and it will have low bias and high variance. Okay. Okay, so this is all about k nearest neighbor distribution. Now there were some techniques that sir discussed. This is for removing this overfitting, right? In the last two that I think I feel is important is no ensemble learning that sir discussed, not overfitting, that ensemble learning, that I feel conceptually it is important. Probably if you are doing research, then only you will be using this at all. But nowadays, as the competition power has increased, I don't think anyone uses these kind of things. These are simple things that you can use. That is, you use weaker models, as sir explained, weaker models, but in a large number to make a stronger model. Okay. So what were the examples? It was bagging and boosting. So we'll try to wrap it up quickly. What is bagging? What is the difference between bagging and boosting? Basically, both follow one similar step, that they use same set of data. What bagging does is, let's first go with the bagging. What it is going to do, it is going to take a sample. So this is your data, training data, and let's say I have 10 10 data points. It is going to train, however, how many number of how many ever number of models you want to train. Let's say I want to train 5 or 4 models. So we have, and each model will have an input of 6 elements. So how will it do that then? We have only 10. So how is it going to give the input of 6 in each model? So it is going to repeat that. And there can be you can actually calculate how to get 6, how many different combinations of 6 you can get from this 10 set of data. So 10c6, if you calculate, so that many combinations can be there, and we just take 4 of them and we give the input. So these inputs can be repeated. So that means that if I have given this particular ALO dot here, then it can actually go here, here, and here also for the training purpose. And this procedure of repeated, like giving the input, selecting the input with repeatability, or sorry, replaceability to the model, to a simpler model for the training and testing, it's called bootstrapping. This process is nothing but bootstrapping. Keeps on erasing, yeah. Bootstrapping. Pardon me if the spelling is wrong. So this is the bootstrapping that sir was discussing in the session. And when you train this, you can train it for a regression, or you can train it for classification. Okay, and whatever output you get, from this model, it is actually going to be the average or the majority of the output. So for average, meaning when you have a regression, then it is going to be the average output for all the models, and when it is classification, then it is going to be the majority. And there comes the limitation of bagging, that it is not going to give you the actual thing, it is going to give you more or less an average output of all these small training models that you are getting. So regression, it is going to give average, and then it is going to give majority in classification. So this is one of the limitations for this model. And what is the main aspect of bagging that differentiates it from boosting? Can anyone tell me? If you were to write, if you were to be asked what is the main difference between bagging and boosting, these ensemble learning procedures or models, then what will be the one point that you have to say? High variance, high bias. So actually, bagging and boosting both are used to reduce the bias and variance. Yeah, but it is not the difference. Yeah. See, these ensemble learnings are used to reduce the bias and variance of these weaker models by combining them together. But I'm asking, what is the main difference between bagging and boosting? Okay, so maybe I have not told boosting till now, that's why it is not clear. But the process of learning, training the trees, are kind of true. So, okay, so the process of learning in bagging of these simpler models runs in parallel, whereas for boosting it is sequential. So, bagging is parallel learning. You can see here what we did, we had a bigger input with us, we partitioned it into different smaller inputs, and they had no they the values were replaceable, so they had similar values also, they can have same value, they can have different value, and then we trained them or we used them in parallel, right? Where and in the bagging, whereas in boosting, how do we train? We train it like this. So you have the same input, let's say you have the same input. Okay, now you put this input into your first model. When you are training this, now let's see, talk about training. Then what you see, some of the portions it has given accurately, it was able to capture the correct values, and some of them it was not able to capture, not give 10, let's say that it is only able to capture 2, whereas all the other 8 were wrong. Then what will happen? We will send the whole thing again, but this time we will give these particular 8 points more weightage, right? So we'll send this input, whereas 2 will have less weightage, and this 8 will have more weightage. And this is the second model. So this was the first one, this is the second model. Now what will happen when we do that? This second model is going to be trained to look at these features separately. Maybe these 8 points are having some features different that the model 1 was not able to capture. So the second model is going to train itself to look at those features separately. More more weightage will be given to those features, and then let's say after that it is able to capture three or four correct values, and the remaining 6 are wrong. So now these 6 will be given more weightage in the new input. So input will be the whole again, but these 6 will be given more weightage. Now this model, the model number 3, is going to be trained in such a way that it is going to give more weightage or more attention to the features that are specially in these things, in these 6. So now you may be able to get a hint that why there might be an overfitting, right? So this will just keep on going, and then you will get a final output. So what can happen is, let's say I am giving you a set of colors, right? Red, green and orange, or yeah, red, green, orange, or some shades of red are also there. So maybe the first one was able to identify all the reds, but then it didn't identify the different shades of red. So the second one, maybe it will try to identify the shades of the red. Then third one will try to identify the shades of green. So this is how sequentially this model is going to work, and each and every aspect of your data it is going to train for. And that is why, since it is individually capturing each and every aspect, if you give a number of n models here, let's say if you give too many models in this sequential process, it is prone to overfitting. So that is like the basic idea, like why, how it is getting prone to overfitting. And yeah, the same thing I will write it here, that these both models are used to reduce bias and variance, but this is prone to overfitting. This is disadvantage, and there are other disadvantages also that you can read from the PPT. This was the main disadvantage. Okay, so that's it for this for today's session. Your week 2 assignment answers are already shared with you. So is there, if there is any contradiction, or you feel that some one of the answer is not correct, then you can ask me and I can try to clarify your doubt. If I'm not able to, I will carry forward the doubt to the professor or the other TAs, and maybe we can work it out.